Never underestimate the power of ellipses. And you can read what's on the slide while I talk. On the Cartesian coordinate system, any point can be represented by two values, x first, y second. If the point is on a circle, we can form a right-angled triangle out of it. O is the y-coordinate of the point, as it is the shortest distance between the x-axis and the point. On the x-axis, all points have a y value of 0. Likewise, adjacent represents the x-coordinate of the point, as it is the shortest distance between the y-axis and the point. On the y-axis, all x values, we can use SOHCAHTOA to find out the true value of x and y. Once we do so, we reach to an equation called x equals radius multiplied by cosine of theta. Y equals to r sine of theta. And we will draw the circle/ellipse using code based on the flowchart shown on the slide. Now we will code the ellipse. We will be using Turtle, a Cartesian coordinate system. We need the trigonometry functions from the math module. This is to make sure that theta, which runs up to 100 times 2 pi, is divided by 100 so that theta will equal 2 pi, so that a full circle is completed. We have 629 divisions here, as the code does not actually reach 630, but rather 629 here. Let's run this and see how it goes. One. And here we draw a circle slowly. We have ways to make this faster. For example, we could do we also don't want to see the turtle. So what happened was I set the speed of the turtle to 0 so that it executes the command as fast as possible, so that it goes to these coordinates in an instant. Tracer to 0 so that we don't see it happening until update is executed. Hide turtle because we do not want to see the turtle, and done to prevent a canvas from closing once the program is done. And we also do not want to see the line from the center to the edge, the radius. So to present that, we will take the pen off the page where the turtle is transferring from the origin to the first coordinate point. We have a circle in this case. We could also do this if we halve radius x, we get an ellipse that is compressed in the x-axis. Let's just reset this. We have this kind of thing. Add, lastly, 0.51200. We can have this type of, if you want to call it, a flower. If we have two ellipses that overlap each other. And I could just make this a propeller if I just reduce the radiuses. And we have a propeller. And if you want even more, is if we want to strictly follow the flowchart that we have given it, so we could do while So basically, theta will be equal to 0, while theta is, is smaller than 2 I. I will delete all of this. Theta plus equals 0, 0, 1. That's the same, and it draws the same thing. And if we want an extension, we could also add a thing called divisions. Although in my other videos I actually call this accuracy. So so going back to the for loop for uh uh, uh go back to here. If we add divisions instead, and I usually use I here, but this time I'll use theta to make it more clear for you. If we use divisions, we could do divisions times 2 times pi. We can manipulate the speed of the ellipse drawing. If we want a more accurate circle, we could increase divisions by, for example, let's say 4,000. The propeller is more accurate, but be careful not to make it too much, or it will just be slow to produce, as you can see here. Check out my other creations. I'll put it up now. To find out how I use this equation to produce all the other shapes that I have shown in the thumbnail.